Hi, and welcome to Chapter 6, Section 2, Part 2. Today we're still looking at volumes of rotated objects, but today we're specifically looking at the washer method. So last time, in the last video, we were talking about the disk method. I didn't actually name it that, but it's technically considered the disk method because you're like finding areas of circles. So if we think about the circle as a disk, then each slice of our cross-section would be a circle, so a disk. In this section, we are looking at the washer method. So it's still kind of a circle. So this is what a washer actually is. It's like when you build stuff, sometimes they include this with the screws and stuff. Not a construction person, so I don't know exactly what these do, but I know it's a washer. So instead of just a circle and looking at the area of a circle now we're looking at the area of a washer. So if you think about the washer as like two circles, if we can figure out the area of the big circle and then subtract the area of the smaller circle, that'll leave you the actual area of the washer itself. So that's our goal here. The problems we would use the washer method for is something like this. So if we had two curves and the shaded area was like this, and then we were rotating it around the x-axis, the rotated shape would look something like this, where it's like hollow in the middle. So because it's hollow in the middle, it's kind of where we get this like center circle part to make that washer. And so as you can see, the overall, like for the big circle, every time we cut into this to make our cross section, it'll make that washer shape because you've got like the overall big circle and then a smaller circle in the middle that you'd take out. But each of those radiuses of the big circle and the smaller circle would change every time depending on the equation of the function itself. And so because of that, we're kind of using the same, it's kind of like how we did the disk method where the radius is actually the equation, just we have two equations to deal with now. So to find the area of the washer and then eventually the area, the volume of the whole entire rotated shape, we would need to find the length of the big radius, so like with the bigger circle, the outside circle, I'm going to use capital R to stand for that, and then a lowercase r for the radius of the smaller circle. So just like how we did last time, the equation of the curve would just be where the radiuses are. And then if that would be the area of one washer, one slice of our cross section, then we can integrate from whatever endpoint to whatever endpoint to then add up all those areas together. So then our overall volume formula would look something like this. The integral from whatever endpoints of, and then I just factored out the pi so that it's like pi r squared minus pi r squared, but pi factored out, and then the bigger radius squared minus the smaller radius squared, and then dx or whatever variable you're using. So for this particular problem, they've given us this curve here is the square root of x. This bottom curve here is y equals x squared. So when we rotate it, the outside of the circle, the outside of our washer, the bigger radius, would be the square root of x function. So for this problem, our bigger radius would be square root of x squared, and then the smaller radius would be the x squared because that's on the inside. And this relates to when we were looking for that area of in between two curves, we did like top curve minus bottom curve. It's a similar process here, the top minus the bottom. So if you want to think about it that way, that also works. So if the bottom curve is x squared, square that, dx. And then our x values go from 0 up until 1, so our endpoints would be 0 to 1. So just simplifying down our equation a little bit, I'm going to move that pi since it's a constant out front, and then my integral is from 0 to 1. Square root of x, squaring that just gives me x. X squared squared is x to the 4th, and then I can integrate this. So I'm going to end up with x becomes x squared over 2, x to the 4th becomes x to the 5th over 5. From 0 to 1, I can plug that in to get 1 squared over 2 minus 1 to the 5th over 2 minus, if I plug in 0, I'm just going to get 0. So then 1/2 minus, oh, this is a 5, not a 2. 1/2 minus 1/5 would be 3/10 as my total volume. There we go. Here's another example where we would have to use the washer method. So here, our equation would be that it's the curve y equals square root of 25 minus x squared. And then our shaded region that we're actually rotating around the x-axis again is bound by the line y equals 3. And then under that curve. So this shaded area right here, if we were to rotate it around the x-axis, your 3D shape would look something like this. So like a bead, I guess, kind of, if something like that. Anyways, so again, similar process here. We know that our bigger radius would be the like top curve, which is that square root of 25 minus x squared. Minus our bottom curve, which is the y equals 3, so 3 squared. And then the pi in front. For this one, our x values are going from, it looks like from the graph, -4 to 4. So those are going to be the endpoints of our integral. So that would be our setup of our integral here. So squaring things out and then combining some like terms, I end up with the integral of pi times the integral from -4 to 4 of 16 minus x squared dx. So this is pretty easy to find the antiderivative of from here. 16 would become 16x, x squared would become x cubed over 3, and then we're plugging in -4 and 4. So from there, so plugging in and simplifying, I end up with a total of 256 over 3 pi. All right, for my last example, I wanted to do something a little bit crazier. So here we go. So this time we are looking at equations of a function that looks like this now. So I'm trying to revolve this shaded region around the y-axis instead. So our rotated shape is going to look like this, but the equations for each of these equations, can't talk. So this curve is supposed to be the equation y equals x squared plus 1. And then to get this bound, or the shaded region, we want to use x equals 1, that line right there to bound it, x equals 0, and y equals 0 to get that shaded region. Okay, so for this one, this requires like kind of a mix of both the washer and the disk method, because the washer method really only applies if we're shading it around, or rotating it around the y-axis. There's really only going to be a washer up until like this point right here, because after that it's just like one solid chunk. So from then on, this is just a disk method because we're not really subtracting anything out of the middle for each of our disks, or each of our slices. So in this case, we want to set up two different integrals then. And because I'm rotating around the y-axis instead of the x-axis, we want to use y values as our endpoints, which means we also need to rewrite our original equation of this curve so that it's in terms of x instead of y. So if I start out with y equals x squared plus 1 and I want to get it in terms of x, I want the x by itself, so I can subtract 1 from both sides and then square root both sides to get x by itself. So when you square root, technically you get the plus or minus, but we only want one side of this because we only want like half that parabola. So really I just need the plus version. So regular square root of y minus 1. So that'll be the equation we use when we're trying to use the washer method for this part. And then our disk method down below, we already know like what the radius is. It's just going to be 1 the whole time because it's just like a cylinder from that point on. So separating these two out, I'm going to just kind of split this in half, I guess, almost. So the bottom part of this weird shape is just going to be that cylinder. So if we think about it as just pi r squared, for this integral from a y value of 0 up until 1, because that's where our parabola starts, and we just want to go up until that point. Then our radius here, since it's constant the whole time, would just be 1. So just pi. And then the antiderivative would be pi x. And then, oh, I forgot the dx. So then plugging in, we would just have 1 pi. Okay, so that's the volume of the bottom. So then the top, I'm going to add this volume to the other volumes with the washer method. On top, I have the integral from 1 to 2, because we're going from a y value of 1 up until 2. And then our outside curve, since we're doing the washer method, the outside curve is actually like this line right here, which is x equals 1. Minus the inside curve, which we said in terms of x was the square root of y minus 1. So then the radius is squared. So using our formula. And then dy instead of dx because we're dealing with y variables now. But pretty much the same. Okay, then simplifying this down, I end up with 1 minus y minus 1, which really simplifies to 2 minus y. And then I can find the antiderivative of that to then find my total volume and then add it to the 1 pi of the bottom part. So my antiderivative is going to be 2y minus y squared over 2 from 1 to 2. So I end up with a volume of 1/2 pi for that top part of our weird shape. So then adding these two, the bottom and the top together, my total volume is going to be 1.5 pi. Or if you want to think about it as 3 pi over 2. Cool. Alrighty. So that's how we do the washer method when we're rotating. And the easiest way to tell when you do washer method is like from the original graph, wherever your shaded region is, wherever you rotate around, if there's a gap at any part, you're going to need the washer method. So that's the easiest way to tell. But that's it. This is my last video for the year. Oh my goodness, can you believe it? But here we are. We've made it. Thank you so much for watching this year. Don't forget to like and subscribe. Share my videos with your friends, anybody else who's taking calculus in the future. Thanks for watching. Bye!